The Mississippi River has shaped the heart of North America for thousands of years, carving an immense pathway through forests, wetlands, fertile plains, and bustling cities before finally emptying into the warm waters of the Gulf of Mexico. Stretching for approximately 2,340 miles, or nearly 3,766 kilometers, it is more than a river. It is an ever-changing geological system, a transportation corridor, an ecological lifeline, and one of the most influential natural forces on the continent. Every day, millions of gallons of water sweep downstream, carrying sand, silt, clay, organic material, and the accumulated history of an enormous watershed that drains nearly 40% of the contiguous United States. Yet hidden within this immense flow lies a process so gradual that it escapes the attention of most observers. The Mississippi has never truly stopped trying to redraw its own map, and despite the appearance of stability, evidence continues to reveal that the river is quietly seeking a different future. Modern satellite imagery presents the Mississippi as a well-defined ribbon flowing confidently towards southeastern Louisiana before reaching the Gulf. Barges move steadily along designated shipping lanes, levees hold back seasonal floods, and cities along its banks appear permanently anchored beside the same watercourse that generations have known. To many people, the river seems fixed in place, as though it has always followed its present route and always will. Geologists, however, recognize an entirely different reality. Rivers of this scale are living landforms, constantly responding to gravity, sediment, erosion, water discharge, and changes in the surrounding landscape. Stability, in geological terms, is often only temporary. The lower Mississippi occupies one of the largest river deltas on Earth, a landscape built grain by grain through countless floods over thousands of years. Every flood deposits fresh sediment across nearby floodplains, gradually raising some areas while abandoning others. New channels begin to form as floodwaters search for steeper and more efficient routes toward the sea. Existing channels slowly become clogged with sediment, while neighboring pathways deepen. These competing processes never truly stop. They unfold over centuries, sometimes millennia, creating a slow but relentless reshaping of the landscape that rarely attracts public attention until dramatic changes finally occur. Long before modern cities appeared along its banks, the Mississippi had already rewritten its own course multiple times. Geological records preserved beneath the wetlands of Louisiana reveal that today's river channel represents only the latest chapter in a much longer history. Ancient sediment layers, fossil remains, buried riverbanks, and abandoned distributaries show that the river repeatedly shifted across southeastern Louisiana, constructing entirely different delta systems before abandoning them in favor of newer routes. These former pathways remain visible today from aircraft and satellites as sweeping arcs across marshes and coastal plains, silent evidence of previous generations of the river. Researchers studying these ancient deposits have identified at least 6 major delta complexes, with some interpretations recognizing as many as 7 distinct systems formed during approximately the past 7,000 years. Each represents a different period during which the Mississippi concentrated its flow through a particular outlet before eventually shifting elsewhere. These include the Teche Delta, the St. Bernard Delta, the Lafourche Delta, and the modern Plaquemines-Belize Delta, among others. Rather than remaining locked within a single channel, the river repeatedly abandoned older pathways whenever a more efficient route developed. This remarkable process is known as river avulsion. Unlike ordinary meandering, where bends gradually migrate across a floodplain through erosion and deposition, avulsion involves the river establishing an entirely new primary channel across its floodplain. During such events, enormous volumes of water begin flowing into a different route, eventually diverting the main river away from its previous course. Although these transformations often unfold over decades rather than overnight, their consequences permanently reshape landscapes, ecosystems, coastlines, and even human civilization. Avulsion begins with subtle changes that accumulate almost invisibly. Rivers naturally transport sediment downstream, but not all of that material reaches the ocean. As water slows during floods, sand and silt settle onto the riverbed and floodplain. Over many years, these deposits gradually elevate the channel above the surrounding land. Ironically, large rivers often flow upon natural embankments. They have built themselves through repeated flooding. As these elevated channels continue rising, nearby lower areas become increasingly attractive escape routes whenever exceptionally large floods occur. Gravity quietly drives every stage of this process. Water always seeks the easiest path toward lower elevations. Even tiny differences in slope can determine where millions of gallons eventually flow. When an alternative route offers a shorter distance, a steeper descent, or less resistance, floodwaters begin exploiting that opportunity. Initially, only a fraction of the river may divert into the new channel. Over time, continued erosion enlarges the opening while sediment accumulates within the older course. Eventually, the balance shifts until the new pathway captures most of the river's discharge. Throughout geological history, this pattern repeated again and again across the Mississippi Delta. Each new channel delivered enormous quantities of sediment into previously submerged coastal waters, gradually constructing fresh land. Marshes expanded, wetlands flourished, and barrier islands developed as sediments accumulated near the river's mouth. Meanwhile, regions abandoned by the river slowly subsided, allowing coastal erosion and saltwater intrusion to reclaim portions of the former delta. Louisiana's modern coastline reflects thousands of years of these alternating phases of land building and land loss. Understanding this natural cycle explains why the Mississippi Delta contains such extraordinary complexity. Rather than being created during a single period, the landscape resembles a layered archive documenting repeated shifts in river position. Ancient distributary channels remain preserved beneath younger deposits. Buried forests mark locations once isolated from active river flow. Thick sequences of clay alternate with coarser sands, recording successive periods of flooding, channel migration, and coastal expansion. Every layer contributes another page to the geological history of one of Earth's great river systems. Among all the potential routes available to the Mississippi today, one stands above the rest in scientific importance. West of the present main channel lies the Atchafalaya River, a distributary whose characteristics have fascinated geomorphologists for generations. Compared with the existing lower Mississippi, the Atchafalaya offers a shorter journey to the Gulf and follows a steeper gradient, allowing water to lose elevation more efficiently. From the perspective of physics alone, it represents an increasingly attractive pathway. Although maps often depict the Mississippi and Atchafalaya as separate rivers, they are closely connected through a complex hydrological relationship that has evolved over centuries. Water has naturally exchanged between these channels for a very long time. During periods of high flow, increasing amounts of Mississippi water have historically entered the Atchafalaya Basin, gradually enlarging its capacity to transport even greater volumes downstream. This relationship reflects precisely the kind of slow redistribution expected during the early stages of river avulsion. Scientists studying river dynamics frequently describe the Atchafalaya as an active capture route. In geological terminology, stream capture occurs when one river gradually diverts flow away from another drainage system through erosion and changing gradients. Unlike dramatic floods that instantly carve new channels, capture often unfolds incrementally, with subtle changes accumulating over many generations before the final transition becomes unmistakable. Every flood contributes a small adjustment. Every deposited sandbar alters local hydraulics. Every season introduces another opportunity for nature to refine the landscape. The attraction between the Mississippi and the Atchafalaya becomes easier to understand when considering the immense energy contained within flowing water. Rivers expend tremendous amounts of energy transporting sediment and overcoming friction along their channels. A shorter route with a steeper slope reduces the effort required to move water towards sea level. Over long periods, such efficiency exerts a powerful influence on channel evolution. Natural river systems consistently seek these energetic advantages whenever geological conditions allow. Historical records indicate that this developing relationship had already become apparent long before modern engineering projects appeared. Explorers navigating Louisiana centuries ago observed connections between the two rivers. Seasonal flooding repeatedly strengthened these links, while natural erosion slowly enlarged connecting channels. The process remained gradual, yet unmistakable to those examining long-term changes rather than isolated events. Each generation inherited a river subtly different from the one known by their predecessors. Hydrologists emphasize that the Mississippi is not preparing to abandon its present channel tomorrow, nor is a sudden overnight diversion currently underway. Instead, the significance lies in recognizing that the underlying geological tendencies have never disappeared. The same natural mechanisms responsible for previous delta shifts remain active today. Sediment continues accumulating. Floodplains continue evolving. Water continuously responds to gravity. The river still seeks equilibrium within an ever-changing landscape, even if human intervention now influences its choices. Much of the lower Mississippi exists within an environment shaped by extraordinary sediment transport. Every year, the river carries vast quantities of suspended material originating from thousands of miles upstream. Rainfall across the Great Plains, snowmelt from northern regions, erosion within agricultural fields, and weathering of ancient rocks throughout the watershed all contribute to this sediment supply. Individual particles may spend months traveling downstream before finally settling within Louisiana's wetlands or reaching the Gulf. These sediments serve both as builders and obstacles. They construct fertile floodplains, supporting agriculture, while simultaneously filling portions of the river channel. Maintaining navigable waterways requires constant dredging because deposition never completely stops. Sandbars emerge, migrate, and disappear according to changing river conditions. Islands slowly grow before being reshaped by later floods. Every movement of sediment subtly alters the hydraulic behavior of the river itself. Flood events play a particularly important role in determining future channel evolution. During exceptionally high discharge, rivers possess enough energy to overflow natural levees and explore neighboring lowlands. Although most floodwaters eventually return to the main channel, some establish temporary pathways that enlarge through erosion. If repeated frequently enough, these pathways can evolve into permanent distributaries capable of capturing increasing proportions of the river's flow. Such gradual adjustments formed many of the abandoned channels still preserved across southern Louisiana today. The enormous flood of the early 20th century marked one of the defining moments in understanding the Mississippi's long-term behavior. Torrential rainfall throughout the watershed combined with rising river levels to produce one of the most destructive floods in United States history. Levees failed across multiple states. Entire communities disappeared beneath floodwaters. Agricultural lands remained submerged for weeks. Hundreds of thousands of people were displaced as water spread across the floodplain on an unprecedented scale. While the immediate humanitarian crisis dominated public attention, engineers and geologists also recognized another alarming reality emerging from the disaster. The river's natural preference for the Atchafalaya River was becoming increasingly difficult to ignore. The observations made after that catastrophic flood transformed the way engineers viewed the lower Mississippi River. Until then, many efforts had focused primarily on containing floodwaters and protecting nearby communities. The flood demonstrated that another challenge demanded equal attention. The river itself was exhibiting the same long-term behavior that had shaped Louisiana for thousands of years. It was not merely overflowing its banks during periods of high water, it was gradually favoring a route that offered a shorter and steeper descent toward the Gulf. Left entirely to natural processes, the balance between the Mississippi and the Atchafalaya would likely continue shifting as erosion deepened the newer pathway and sediment slowly accumulated within portions of the existing channel. Hydraulic measurements collected during subsequent decades confirmed these concerns. During periods of elevated discharge, increasing amounts of water naturally attempted to enter the Atchafalaya system. Engineers understood that this was not a temporary anomaly caused by a single flood season. It reflected a fundamental characteristic of river evolution. Whenever two connected channels compete for the same flow, small differences in slope, channel geometry, and sediment transport gradually influence which pathway becomes dominant. Once one route gains an advantage, the increased discharge often accelerates erosion, enlarging that channel and attracting even more water in a self-reinforcing cycle. For communities along the present lower Mississippi, the implications of an uncontrolled avulsion would be enormous. Cities such as New Orleans and Baton Rouge developed because of their direct relationship with the river. Their ports depend upon deep navigation channels capable of accommodating large commercial vessels transporting grain, petroleum products, chemicals, steel, and countless other commodities between the American interior and global markets. Billions of dollars in economic activity rely upon maintaining that connection. If the Mississippi naturally shifted most of its flow into the Atchafalaya Basin, the existing navigation channel downstream of the diversion point would gradually lose discharge. Reduced flow would encourage sediment accumulation, making navigation increasingly difficult and fundamentally altering one of North America's most important transportation corridors. Recognizing these risks, the United States Army Corps of Engineers undertook one of the most ambitious river management projects ever attempted. Rather than allowing nature to determine the balance between the two rivers, engineers designed a system intended to regulate exactly how much water entered each channel. Their objective was neither to eliminate the Atchafalaya nor to completely isolate it from the Mississippi. Instead, the goal was to preserve a carefully controlled distribution that would maintain navigation, reduce flood hazards, and prevent an abrupt reorganization of the lower river system. The result became known as the Old River Control Structure, a complex network of gates, spillways, locks, and supporting infrastructure located where the Mississippi and Atchafalaya are connected. Its function appears deceptively simple, yet the engineering challenge behind it is extraordinary. Every day, operators manage one of the continent's largest river systems by controlling how much water continues down the Mississippi and how much enters the Atchafalaya. Under normal operating conditions, approximately 70% of the combined flow remains within the Mississippi, while roughly 30% is directed into the Atchafalaya. Maintaining that balance requires constant monitoring because river discharge changes continuously with rainfall, snowmelt, seasonal flooding, and sediment movement across the vast watershed. The importance of this structure becomes clearer when viewed through the lens of geology rather than engineering. Nature continues encouraging the Mississippi toward the Atchafalaya because the physical advantages of that route have not disappeared. The river still recognizes the shorter distance and steeper gradient through the laws of fluid motion. The control structure does not erase those geological tendencies. Instead, it continuously counters them through human intervention. Every gate adjustment represents an ongoing effort to hold the river within a configuration that differs from what natural processes might eventually produce on their own. Maintaining this delicate balance is far from effortless. High water events place enormous stress upon every component of the system. During major floods, billions of cubic feet of water exert tremendous hydraulic forces against concrete walls, steel gates, and surrounding embankments. Engineers must carefully regulate releases to prevent excessive pressure from damaging critical infrastructure, while simultaneously ensuring that downstream communities remain protected. Decisions often involve balancing navigation, flood control, ecological considerations, and structural safety under rapidly changing conditions. The challenge extends beyond water alone. Sediment behaves differently depending upon flow velocity, channel depth, and turbulence. Faster-moving water can transport larger particles over greater distances, while slower currents allow material to settle onto the riverbed. As operators regulate discharge between the Mississippi and the Atchafalaya, they also influence where sand, silt, and clay accumulate. These sediment patterns gradually reshape channels over time, meaning that today's hydraulic conditions inevitably affect tomorrow's river geometry. This interaction between flowing water and transported sediment lies at the heart of river science. Rivers are not simply conduits carrying water from inland regions to the sea. They are dynamic systems continuously constructing and destroying their own pathways. Every grain of sand deposited along a bank slightly changes the local current. Every eroded bend alters water velocity downstream. Millions of these tiny adjustments combine over decades into measurable transformations of the landscape. Although individual changes may seem insignificant, together they determine whether channels deepen, migrate, or eventually become abandoned. Satellite observations collected over recent decades reveal that these processes remain active throughout the lower Mississippi basin. Sandbars continue shifting position, side channels expand and contract. Wetlands gain sediment in some locations while losing elevation in others. Meanders slowly migrate across portions of the floodplain. None of these changes indicate that the Mississippi is presently abandoning its established navigation channel. Instead, they demonstrate that the river remains an evolving geological system despite extensive human management. In a nutshell, changing course requires careful scientific interpretation. Many people imagine a river abruptly carving an entirely new valley within days or weeks. That image bears little resemblance to the Mississippi's present condition. The river's main navigation channel remains where maps show it because engineering infrastructure actively preserves that arrangement. Yet, from a geomorphological perspective, the forces capable of producing future avulsion have never disappeared. They continue operating quietly through sediment deposition, channel migration, floodplain evolution, and the persistent hydraulic attraction of the Atchafalaya River. Understanding this distinction is essential because it separates dramatic misconception from measurable geological reality.